Okay, so good morning, guys. Let's start the meeting. Is the screen visible to all of you guys? Is the screen visible?
Yes, sir.
Okay, fine. So today we'll start with another reaction, which is very important reaction. It's called diazo coupling reaction. Probably in the last class I talked about this reaction. So in this reaction, diazo means we have got two nitrogen atoms in the molecule. Okay, so diazo compounds means like this kind of compound, like benzene diazonium chloride. This means compound can be treated as a diazo compound. So how can we synthesize this compound, benzene diazonium chloride? So we'll have to start with a compound called nitrobenzene. Okay, so nitrobenzene means what? Nitrobenzene is basically C6H5NH2. So first of all, what we will do is we will perform the reduction of nitrobenzene into aniline. So how can we accomplish this? In order to accomplish this task, what we will do is we'll use either a mixture of SN and concentrated HCl, or we'll be using zinc and concentrated HCl. So these are the two combinations we have in our hand. So we can choose any one of these two. So following the high means reduction reaction, will end up with a compound called aniline. Aniline is basically C6H5NH2, right? So now our task would be to convert aniline into benzene diazonium chloride. So how can we do so? We can do it by using a mixture. Okay, what is the mixture we are talking about? Here it's a mixture of sodium nitrite and dilute HCl. And what would be the reaction temperature here? So the reaction temperature would be around 0 degrees Celsius. So following this reaction, we'll have a compound called benzene diazonium chloride. Okay, so here the reaction doesn't stop. So next step would be what? Next step we'll be using another reactant, okay, in order to form a diazo compound which has got industrial relevance. So what would be the compound? Can anybody tell me? In the last class, I talked about the name of this compound. First of all, we will have benzene diazonium chloride. So benzene diazonium chloride thus produced following these two steps. Okay, will interact with another compound to form diazo compound, which has got industrial relevance. So what would be the another reagent over here? I talked about it in the last class. Any answers? Any guesses rather? Okay, so here is that compound. So benzene diazonium chloride I have already have, and the another compound is dimethyl aniline. Forget about these three CH3 groups. Okay, so why is it called dimethyl aniline? Aniline is C6H5NHH. So here both the H are being replaced by CH3 groups, two CH3 groups. Okay, so that's why this compound is called dimethyl aniline. Okay, so following the reaction between these two, will end up with a azo dye like this. It's very simple. What will happen is here we have got one hydrogen atoms, right? So this hydrogen atom will interact with this chlorine atom of benzene diazonium chloride, producing this kind of structure. So this is called the azo dye. And what would be the byproduct of this reaction? The byproduct of this reaction would be HCl. Okay. So now the question comes, means where we can utilize this kind of azo dye. Can anybody tell me what is the means application end application of azo dye? And by the way, let me tell you that this kind of reactions are being conducted in the dye manufacturing industries. Okay, in the dye manufacturing industries. And what are the typical sources of the dye molecules? Any idea? Suppose I have got an industrial effluent, and the industrial effluent is rich in dye compounds. That means the industrial effluent has got certain amount of dye compounds, like it can be either methylene blue, okay, crystal violet, methyl blue, rhodamine B. These are the typically used dyes. So these are the dye compounds. So we can have, means in most of the chemical industries effluent, if we take out certain amount of effluent and we carry out the analysis, we'll find that there are existence of different kinds of dye molecules in the effluent of the process stream. Okay, so what could be the typical industries?
Textile.
Textile industry. What else? Yeah, it's a correct answer. Any other industries?
Paper.
Like tannery industry also.
Yeah.
So there are several other industries, but I want you to tell me the names of those industries. Okay. So in the die manufacturing industry, for the timing, remember that we carry out this diazo coupling reaction in the die manufacturing industries. Okay, so the next reaction I'll be talking about, this is also a very important reaction called condensation reaction. Okay, so what is condensation reaction? Am I audible to all of you guys?
Yes, sir.
Okay, okay, fine. So next is the condensation reaction. So for condensation reaction also, we need to have two different types of reagents or reacting species rather. So what could be the typical reacting species here? Here, one reactant is C6H5CHO, right? We all know, right, what is benzoic acid? Benzoic acid is basically C6H5COOH, and benzaldehyde means C6H5CHO. This is an aldehyde compound. Okay, so this is the benzaldehyde. So this is the chemical formula of benzaldehyde, like C6H5CHO. And another aldehyde compound we are using here is acetaldehyde. Acetaldehyde means CH3CHO. So we allow both of them to interact in the presence of sodium hydroxide. Okay, so sodium hydroxide acts as a catalyst over here, and as a result, we end up with two compounds. One is called the cinnamaldehyde. Probably you all of you remember what is cinnamaldehyde. Cinnamaldehyde is basically C6H5CH double bond CH single bonded CHO. This is called cinnamaldehyde. And along with cinnamaldehyde, we get another byproduct of this reaction. So what could be the typical byproduct of this reaction? So typical byproduct would be H2O, water molecules. Okay, so cinnamaldehyde we produce, and probably you all remember that first of all we start with an alcohol. Alcohol get oxidized into aldehyde, and further it reoxidizes to acid. In the reverse manner, if we talk about acid, so acid means if we perform the in a reduction reaction of acid, so what will happen is acid will get converted into either aldehyde or ketone, and for further reduction will means lead to the formation of the alcohols, right? So here we have got cinnamaldehyde. So aldehyde compound we have, suppose we are performing the oxidation of this cinnamaldehyde. So what would be our typical end product? So our typical end product would be cinnamic acid. Okay, in the dye manufacturing industry, we use cinnamic acid. Okay, so cinnamic acid has got a chemical formula of C6H5CH double bonded CH single bonded COOH. Okay, so this is the cinnamic acid. So can anybody tell me what could be the oxidizing agent here? There are several oxidizing agents one can use for the interconversion of cinnamaldehyde into cinnamic acid, or maybe a aldehyde into a acid. So what could be the typical oxidizing agent here? In order to convert aldehyde into acid, we can have different types of oxidizing agents, right? So can anybody tell me one example of such like oxidizing agent?
Peroxide.
What type of peroxide you are talking about?
Hydrogen peroxide, I guess. Or
It's a,
or permanganate. If you,
potassium permanganate plus what?
um, I don't remember.
It could be alkaline KMnO4, okay?
Uh,
Or it could be a mixture of potassium K2Cr2O7 plus H2SO4, right? Potassium dichromate plus H2SO4. This can act as an oxidizing agent. Either means we can use this, or we can also use alkaline KMnO4. Alkaline KMnO4 acts as an oxidizing agent. Okay, so in order to convert cinnamaldehyde into cinnamic acid, we'll either use alkaline KMnO4 or a mixture of K2Cr2O7, that means potassium dichromate and concentrated H2SO4. Okay, so this was the one example of condensation reaction. So in the condensation reaction, we end up with one byproduct. If we remember the condensation polymerization, then also we talked about one reaction where we had like what we had there. We had adipic acid and hexamethylene diamine. Following this reaction, we also ended up with H2O. There was another example where I showed you how to synthesize alkyd resin. So what was the byproduct of that reaction? Byproduct was H2O. So here also we have got similar kind of byproduct. So what is our byproduct here? It is H2O. Okay, so this is basically a condensation reaction. In the dye manufacturing industries, we make use of this condensation reaction. So let us talk about another example of condensation reaction. This reaction is also very important and very common reaction. So first of all, we will start with phthalic anhydride. Okay, so phthalic acid is what? C6H5, COOH. So how can we convert acid into anhydride? Anhydride means we remove the H2O molecule from the acid. So here also we had like COOH. This was phthalic acid. So from phthalic acid, following the removal of H2O molecule, we ended up with C6H5, C double bonded O, C single bonded O. Again, C is attached to O single bondedly, and C is attached to another oxygen atom with a double bond. Okay, so this is a chemical formula of phthalic anhydride. You need to remember this formula. Okay, in the exam, I will ask you how to convert phthalic anhydride into anthraquinone. Then you will have to write this equation. Okay, so you practice by yourself. Okay, it's not that difficult. So if you practice once or twice, things will be clear to you. So phthalic anhydride will interact with the simplest aromatic compound. What could be our simplest aromatic compound? It's benzene. Benzene is the simplest aromatic compound, right? So it interacts with benzene, producing this kind of complicated structure. So what is the name of this compound? This compound is basically anthraquinone. Okay, so this reaction is also not that difficult. See, here carbon is attached to one oxygen. Here also this carbon is attached to the same oxygen. And in benzene, this carbon is attached to one hydrogen. Okay, and this carbon is attached to one hydrogen. So what will happen is H and O, they will interact with each other, producing this compound plus H2O. It's not that difficult. If you practice by yourself, things will be clear to you. Okay, so I'm repeating again. So we have got phthalic anhydride. Phthalic anhydride has got a chemical formula of C6H5, C double bonded O, C single bonded O. Again here C double bonded O, C single bonded O. So this is the chemical formula of phthalic anhydride. So phthalic anhydride interacts with benzene. Benzene has got a chemical formula of C6H6. Okay, so it has got a ring structure. So this carbon is attached to one hydrogen. All the carbon atoms in the ring, that means it's a 6-carbon ring. Okay, so each carbon atom is attached to one hydrogen atom, right? So here two hydrogen atoms, like one hydrogen atom attached to this carbon and another hydrogen atom attached to this carbon will interact with this oxygen atom, producing H2O. And what would be the main product of this reaction? The main product of this reaction would be anthraquinone. Okay, so this also comes under condensation reaction. Okay, so here are the two examples of condensation reaction. So I want you to remember both the reactions, since in the exam I can ask either this one or that one. Okay, or maybe I'll ask some conceptual question based on these two equations. Okay, so now coming to the calcination reaction. Hopefully you remember, right? What is calcination reaction? Without looking at these examples, can anybody tell me what is the proper definition of calcination reaction? Yes. What would be the proper definition of calcination reaction? And why is it necessary to perform such kind of reaction? Here I have already noted down that in the cement industries, we make use of calcination reaction.
Then I guess heating to high temperatures with
Heating to?
high temperatures with
So you need to specify the temperature. High temperature means it could be 500 degree, 400 degrees, 600 degree, as high as 1700, 800 degrees. So while talking about the high temperature, you need to specify the temperature.
I guess below melting.
Below the melting point. Yeah, it's a correct answer. Okay. So calcination operation means we need to, suppose I have got a compound called CaSO4, okay, or CaNO3 whole twice. Calcium nitrate, calcium sulfate. These are the two compounds I have. I want to convert them into the oxide form. So how can I do so? I can carry out this means conversion by a method called calcination. So what is calcination? Calcination is basically the heat treatment at a certain temperature that depends on the melting point. So every time we need to carry out the calcination below the melting point of the parent molecule. Suppose I'm starting with calcium nitrate. So I'll have to choose one temperature. This temperature we cannot choose by ourselves. There are some reactions we need to perform in order to get to know what would be the optimized calcination temperature. Okay, so there is a method called temperature programmed reduction analysis. Those who work in the catalyst field, they all know what is temperature program reduction analysis. It's nothing like what we do is we carry out the, first of all, we calcine the material at various temperatures. Let's say the material has got a melting point of about 700 degrees Celsius. So what people generally do is they calcine the material. That means they heat treat the material at a temperature of around 100 degree, 200 degree, 300 degree to 700 degrees Celsius. So you have got a product. So what next step is, in the next step, what people do is people allow, means people take this certain amount of material, say for example, 100 milligram of that material is placed inside a U-tube quartz cell, okay? And after that, what people do is they purge hydrogen, 5% hydrogen in 95% nitrogen through this material and allow the reaction to continue from room temperature to a certain temperature, let's say 900 degrees Celsius temperature. Okay, so at a certain point, we'll get a peak. So we'll have to take that peak maxima. Okay, for calcium, suppose I'm using calcium nitrate. So calcium nitrate has been calcined at a temperature between 100 and 700 degrees Celsius. Let's assume the melting point of calcium nitrate is 700 degrees Celsius. But I don't know what would be the optimized calcination temperature. So how can I do so? What I'll do is I'll take certain amount of, let's say 100 milligram of that calcined material in a U tube. Okay, it's made up of quartz. Since I'll carry out the reaction at a temperature of around 900 degrees Celsius, starting from room temperature at a temperature ramp of 10 degree per minute. Temperature ramp means I will increase at a rate of 10 degree per minute. Okay, there is a PID controller. It's a very sophisticated instrument. The instrument is called TPR analyzer. Okay, so what it will utilize is, what would be the TPR probe molecule? TPR probe molecule would be 5% hydrogen in 95% nitrogen. That means I'll use a gas mixture. What would be the mixture comprised of? The mixture will be comprising of 5% hydrogen and remaining 95% nitrogen. Okay, so I'll purge 5% hydrogen through that quartz tube, and I'll allow the reaction temperature to increase from room temperature. So let's say room temperature is 30 degrees Celsius. So from 30 degree to 900 degrees Celsius. So during this reaction, and I'll monitor, okay, and the outlet of this reactor is connected to a TCD detector. TCD detector means thermal conductivity detector. Okay, this will detect the formation of any gas or any product in the, and it will record this. So what I'll find is, at a certain temperature I'll find a peak. Okay, so I'll get the peak maxima. If I've got a peak, immediately I can get an idea what would be our peak maxima. So at that peak maxima, we'll carry out the calcination reaction. So that would be our optimized calcination reaction. So how to calculate the optimized temperature? So means I have got peak maxima at different temperatures. I have calcined the material starting from 100 to 700 degrees Celsius, and peak maxima I'll be recording for each and every temperature. Okay, and what we'll do is, the area under the peak I will consider. Suppose I have calcined the material from a temperature between 100 and 700 degrees Celsius, assuming that calcium nitrate has got a melting point of around 700 degrees Celsius. So at various temperature, means I will calcine the material at various temperatures. So at various temperatures, I will get different peaks. Okay, and the area under the peak I will be considering. Suppose at 500 degrees Celsius, I have got more area under the peak. Okay, so the calcination temperature would be that temperature, 500 degrees Celsius. Okay, so now calcination can be performed in the presence of oxygen or in the absence of oxygen also. That depends on the type of material we are handling. Suppose our material is not non-carbonaceous. Okay, so that means our material doesn't have any carbon content. Then we can go for oxygen medium. Okay, so suppose I have got only calcium carbonate. I want to convert calcium carbonate into calcium oxide and carbon dioxide. So what would be our typical temperature? Typical temperature is around 500 degrees Celsius. But remember one thing, we are carrying out this reaction in the absence of nitrogen or any inert atmosphere. Okay, since it doesn't have any carbon content here, so we don't need to carry out this reaction in the inert atmosphere. Since inert atmosphere, creating inert atmosphere is expensive. Helium, argon, or nitrogen, these are expensive, right? But oxygen is means readily available everywhere. So we don't need to carry out this reaction in the presence of any inert atmosphere if our material is non-carbonaceous. So suppose I'm handling calcium carbonate, I need to convert this calcium carbonate into calcium oxide. So how would I do it? I will heat the material at a temperature of around 500 degrees Celsius in oxygen atmosphere to get calcium oxide, and CO2 will evolve out of the system. But if I have got a carbonaceous support material, okay, I'll talk about this while teaching you how to synthesize supported catalyst and all. But for the time being, remember that I have got a carbon material, and on carbon top of carbon material, I have got dispersion of calcium carbonate. Like I have got calcium carbonate particles. These calcium carbonate particles are dispersed on the surface side of carbon. So what will happen is I cannot carry out the reaction at a temperature of around 500 degrees Celsius in the presence of oxygen. What will happen is at 500 degrees Celsius, much below 500 degrees Celsius rather, the carbon will interact with oxygen, producing carbon monoxide and carbon dioxide. If it is incomplete means combustion, then we will get carbon monoxide. But if it is complete combustion, then we'll get carbon monoxide plus carbon dioxide. Here carbon monoxide percentage would be quite less. However, we will get mainly carbon dioxide. So in order to avoid that, what we will do is we'll carry out the same reaction at a temperature of around 500 to 550 degrees Celsius. Instead of using oxygen atmosphere, here we will switch to either nitrogen atmosphere or helium atmosphere or argon atmosphere. Okay, in the inert atmosphere, what happens is it will prevent the excessive burn off of the carbonaceous material. Okay, so in order to avoid the excessive burn-off of the carbonaceous material, we cannot carry out the calcination reaction in the oxygen atmosphere or in air atmosphere. Okay, if our means carbon is getting converted into carbon monoxide and carbon dioxide, finally we'll end up with only calcium oxide, which we don't want. We want calcium oxide on the surface of carbon material, right? If the support goes off in the form of carbon monoxide and carbon dioxide, this material would be of no use to us. So in order to avoid that, what we'll do is we'll carry out the calcination reaction in the presence of an inert atmosphere when I have got carbonaceous material in my hand. Okay, so suppose I have got carbon support. Support means, let's assume we have got carbon particles, micron-sized carbon particles. So on top of micron-sized carbon particles, I have got calcium carbonate particles. Okay, calcium carbonate is also micron-sized particles. So I will carry out the calcination reaction. That means the heat treatment. Calcination is sometimes called as heat treatment. Okay, so heat treatment, we carry out the heat treatment at a temperature of around 500 degree or 550 degrees. That means there is a range between 500 and 550 degrees Celsius. So we'll end up with a compound called calcium oxide on carbon material. Provided we can get this kind of material if we have got any inert atmosphere. Suppose we are performing this, we are trying to perform this reaction in the presence of oxygen or air atmosphere, we can't achieve this kind of product. We'll get only calcium oxide instead of calcium oxide supported on carbon. Why is it so? Since in the air or atmosphere, oxygen atmosphere, this carbon will burn off and it will produce a mixture of carbon monoxide and carbon dioxide. If I have got incomplete combustion, then I'll get mainly carbon monoxide. But for the complete conversion at 500 to 550 degrees Celsius, we expect the complete combustion, okay, of carbon material. So it will produce a mixture of carbon monoxide and carbon dioxide. However, the concentration of carbon dioxide in the mixture would be quite higher. Okay, and the concentration of carbon monoxide would be quite less. Okay, so in order to avoid that, we'll use the nitrogen atmosphere or helium atmosphere or argon atmosphere if we are handling a carbonaceous material for the calcination operation. Is this clear to everyone?
Yes.
Yes, sir.
Okay. So this was calcination reaction. In the cement industry, we need calcium oxide. So we first of all start with calcium carbonate. Calcium carbonate is easily available. So in order to convert calcium carbonate into calcium oxide, we make use of calcination reaction. So calcination reaction is nothing. It's just heat treatment at a certain temperature in the air atmosphere. Especially suppose we're handling carbonaceous material, always remember, instead of using oxygen or air atmosphere, we'll have to switch to an inert atmosphere. So what could be our inert atmosphere? It could be either nitrogen atmosphere or helium atmosphere or argon atmosphere. Okay, so now coming to another very important concept, which is catalytic cracking. I'll be talking about catalytic cracking in more details while teaching you the petroleum refinery industries. Okay, but for the time being, remember what is catalytic cracking. Can anybody tell me what is catalytic cracking? Probably you have heard of this term, catalytic cracking. Now I am giving you a brief introduction of different types of reactions. However, I'll have to talk about these reactions in detail. Okay, in different means like chapters, like for sulfur and sulfuric acid manufacturing, I'll be talking about the contact process and all. When process flow diagrams will also be explained. Okay, in petroleum refinery, not only catalytic cracking, catalytic reforming, cyclization reaction, isomerization reaction, those reactions will be taken care of. And then I'll be talking about those reactions in detail. But for the time being, just to tell you what is catalytic cracking, I'm showing you this kind of examples. Okay, so now tell me what is catalytic cracking, if you have got any idea about it.
So
So
breaking
breaking
long
long
chain
chain
hydrocarbons
hydrocarbons
into
to
smaller
small
chains
chains
by
by
heating.
heating.
Yeah, so is it a means like a catalytic process or non-catalytic process? Your answer was
Catalytic.
and not every time it is not catalytic cracking. There is a method called thermal cracking also.
Okay, yes, sir.
Okay, so there are two different ways by which we can study the cracking operation. One is called thermal cracking. For thermal cracking, we need slightly higher temperature than the catalytic cracking reaction. Okay, so there are two different types of cracking reactions. One is called thermal cracking and the other one is called the catalytic cracking. So for the time being, let's remember what is catalytic cracking. So let's assume we are starting with a compound called CCCCC. So this is basically a long chain. Okay, paraffinic compound. Paraffinic compound means they are saturated compounds. They don't have any like unsaturated groups or unsaturated bonds like double bond or triple bond. It doesn't contain. So these are basically the paraffinic compound. So this is saturated compound. Let's assume I'm starting with a 6 carbon long chain molecule. Okay, so this is 1, 2, 3, 4, 5, 6. So this is 6 carbon, right? So if the long chain has got 6 carbon, so somebody just now told that when we have got a long chain molecule, that will get converted into small chain molecules. Okay, so what will happen is, let's assume we are starting with C6 compound. So breakage will take place or cracking will take place from here. Okay, so we'll get two equal halves. Two equal half means if small fractions, there will be two different fractions. There could be more fractions as well. But first, in the first step, what will happen is they will get converted into small chain molecules. But in the small chain, if the parent molecule has got 6 carbon atoms, in the small chain molecules, we'll have 3 carbon atoms. Okay, so each molecule will have 3 carbon atoms. However, there will be a formation of one saturated compound and the another one would be the unsaturated compound. So this is the beauty of catalytic cracking reaction. Okay, so they can further be cracked into more smaller fractions. But for the time being, let's remember we are starting with a 6-carbon long chain paraffinic compound and following catalytic cracking operation at a certain temperature. Let's assume it's around 450 or 500 degrees Celsius. Okay, in the presence of a catalyst. For catalytic cracking reaction, we can use different types of catalysts. Okay, so what could be our typical catalyst? It can be either nickel-based catalyst, nickel supported on silica, nickel supported on silica alumina, nickel supported on alumina. Okay, what is alumina? Alumina is basically Al2O3. What is silica? Silica is basically silicon dioxide. That means SiO2. What is alumina silica? These are basically the supports. Okay, so alumina silica has got a chemical formula of Al2O3 slash SiO2. Okay, so it's a mixture of alumina plus silica. Silica means SiO2, alumina means Al2O3. So it's a mixture of alumina, silica, alumina is a mixture of alumina and silica. And silica has got a chemical formula of SiO2, that means silicon dioxide, and alumina has a chemical formula of Al2O3. Okay, so these are the typical catalysts. However, these days we are using different other types of catalysts also. I'll talk about those things in detail while teaching you the catalytic cracking operation. Okay, but for the time being, remember I have got a long chain paraffinic compound present in the feed, and this compound is getting cracked into 2 equal halves. However, one half is paraffinic and another half is basically unsaturated. Why is it called unsaturated? Since here we can see a double bond. So if the compound has got existence of a double bond, it cannot be treated as a paraffinic compound. So it would be treated as an unsaturated compound. So 6-carbon member getting cracked into 3-carbon member. One is paraffinic and another one is unsaturated compound. Okay, so in the petroleum refinery, we basically make use of this reaction. By the way, you tell me one thing, do you have any idea what is support, what is active metal? These concepts, these things are clear to you. Have you ever studied like chemical reaction engineering, this course? You have studied
Yes.
this course, right? Chemical reaction engineering.
Yes.
Okay. So probably you know what is support or what is active metal, or should I repeat those things again? I think I should repeat it again if everybody is not if they don't know about these things. Okay. Support means we have got a material which doesn't have that much surface area. It can have moderate to high surface area, though we are talking about high surface area, but high surface area support material with high surface area can be achieved only for the carbonaceous materials. Let's assume we are considering activated carbon. Activated carbon is black carbon particles. Okay, so activated carbon has got a high high surface area. What could be the typical surface area of activated carbon? It could be as high as 1000 to 1200 meter square per gram. Okay, this is how we represent the active surface area in meter square per gram. So activated carbon has got a surface area of around 1000 to 1200 meter square per gram. Okay, there are another carbonaceous supports also. One is called the carbon nanotubes. Have you ever heard of this term, carbon nanotubes? They are basically tubular shaped carbon particles. Okay, they also have got high surface area, like around 700 to 800 meter square per gram. Graphene, have you ever heard of? What is graphene? Graphene is again a 2D means carbonaceous material which has got surface area as high as 2000 meter square per gram. So these are basically considered as the support material. This comes under the carbonaceous support material. If I talk about the non-carbonaceous support materials, non-carbonaceous support materials could be alumina, silica, silica alumina. I just talked about these 3 compounds, right? There could be some other non-carbonaceous support materials as well. They can be either titania. Titania is TiO2. Okay, zirconia. Zirconia is ZrO2, and so on. Okay, zeolite also comes under the non-carbonaceous support material. So support materials is it has got high surface area. This high surface area facilitates the facilitates the dispersion of active metals. Let's assume I am considering one catalyst called nickel on silica. Here nickel is basically our active metal and silica is our support material. I think I should show you some of the images. Then it will be means easier for me to make you understand what is basically support and what is the active metal. Okay, so just a second. Okay, can everybody see these images? Hmm?
Yes, sir.
Yes, sir. You can see it, right? So these are basically the scanning electron microscopic images of platinum nanoparticles. Okay, platinum is I mean, we generally don't use platinum that much since it's a novel metal and it is very expensive to prepare platinum-based catalyst. But however, in certain reactions, we cannot use any other active metals. We have to use platinum-based materials. Okay, so platinum gives us high yield or high selectivity of the desired product. Okay, so in such cases, we use platinum-based nanoparticles as an active metal. However, in most of the cases, we generally go for the transition metal-based catalyst. Like transition metal means it can be nickel, okay, it can be iron, it can be cobalt, sometimes zinc, copper also comes under this category. Okay, so these are basically the active metals. Platinum is basically active metal in this case, and here we are having two different kinds of support materials. One is silica support, another one is alumina support. Let's first talk about the silica based support material. So first, considering a case where I have got a catalyst where silica acts as a support and platinum acts as a active metals. So here, can you see these spheres, big spheres, these spherical shape particles? Look at the cursor. Okay, so these are basically the silica support. Okay, these are basically the silica support. And on top of silica support, probably you can see the active metals. The shiny white particles are basically the active metals. These small shiny particles. Can you trace these particles? You can see it, right? These small particles, shiny white shiny particles.
Yes, sir.
Yes, sir. So these white shiny particles, these small white shiny particles are basically the active metals. So here in this case, what is our active metal? Here our active metal is platinum. Okay. And what is our support material? Support is silica. Silica support is basically, it has got a spherical shape, but the shape would be quite big. Okay, it's quite bigger compared to the active metal. So active metal are basically these shiny, white, shiny, small particles. So these are the active metals supported on a silica support. Okay, so here we can see the dispersion means what do you mean by dispersion? Tell me. You have studied this in chemical reaction engineering. What is called dispersion? You'll have to tell me, okay, what is dispersion? So these are basically these big particles are basically the silica support. Okay, so if suppose I have got bare silica support without any platinum nanoparticles in it, then what will, if I take certain amount of silica support and put it under an electron microscope, I'll see this kind of spherical shaped particles, these big particles. Suppose now I have prepared platinum nanoparticles on silica support. Then the image will look like this. So here you can easily distinguish, you can make the distinction between two different types of particles. One particle is bigger, so these are basically the silica supports, and another small shiny white particles. So these are basically the platinum nanoparticles. So here you can see a dispersion of or distribution of platinum nanoparticles on the surface side of silica support. Okay, so this is one example of a supported catalyst. So platinum supported on silica. Okay, so here this is an example or scanning electron microscopic image of platinum nanoparticles dispersed on silica support. Let's move to another example. So platinum nanoparticles dispersed on alumina support. Here it will be very easier for you to understand. So first of all, let's talk about this left-hand side image shown in the left-hand side. Okay, so this image is basically the scanning electron microscopic image of alumina support. Okay, so this is how the alumina support looked like. But suppose I have got dispersion of platinum nanoparticles on the surface of alumina support. So how would the morphology look like now? So this is how the morphology will look like. Okay, so you can see this support, and on the top of this support we can see white shiny particles, isn't it? We can see white shiny particles. These two images are different, right? Here also the background remains the same. However, on top of this background, we can see white shiny particles here and there, distributed here and there on the surface of this. So these white shiny particles are basically the platinum nanoparticles. Okay, so this is a perfect example of platinum nanoparticles on alumina support. So this is also an example of supported catalyst. Suppose I'm only handling platinum nanoparticles, and instead of having this kind of images, I will just find this small shiny particles. Nothing else I'll see here if I'm just considering the platinum nanoparticles. Okay, on alumina support. So this is how the alumina support, the morphology of alumina support will look like. But on the surface side of alumina, if I have got platinum nanoparticles, so this is how the morphology look like. So here I have got means alumina support. This is the alumina support is basically the background here, and on top of that I have got dispersion of these white shiny small shiny particles. Okay, so these small shiny particles are basically platinum nanoparticles. I can also confirm these particles to be the platinum nanoparticles by an measurement or analysis, which is basically a EDS analysis. EDS analysis means energy dispersive X-ray spectroscopic analysis. By this analysis, we can easily trace the presence of platinum nanoparticles on the surface of a alumina support. Okay, for the time being, let's just remember this, and I will go into the detail of it later. Okay. Okay, so now again coming back to the catalytic cracking part. So now we know what is support and what is the active metal. So in that case, platinum was the active metal and support was the silica nanopart, silica and alumina. So I have shown you two separate images where in one case we had silica as a support, and on top of silica we had dispersion of platinum nanoparticle. In one another example, I showed you the same image of alumina support, and on top of that white shiny particles I could see, and those particles were basically the platinum nanoparticles. Okay, so now probably it is clear to you what is support and what is the active metal. So here I have shown you a pictorial representation of a support. This is our support, and on top of the support I have got dispersion of active metals. Okay, so these are basically our active metals. Okay, these spherical small spherical particles, these are basically our active metal, and here this is our support material. So what could be our active metal? Yeah, I told you previously that in most of the cases we will be using transition metal based catalyst. Why is it so? Since it's not that expensive to produce such kind of catalyst. Suppose we are handling means noble metal based catalyst. Noble metal based catalyst could be what? It could be either platinum or rhodium or palladium. Okay, sometimes gold is also a noble metal based catalyst, but handling those materials is not that easy. Okay, it's also very expensive to synthesize such kind of materials. However, in some cases we'll have to use platinum based or noble metal based catalyst to improve the yield of the desired product. But in most of the cases nowadays, people are mainly using transition metal based catalyst. Okay, so why is it so? Can anybody tell me why people are generally using transition metal based catalyst nowadays? What is the advantage of transition metal based catalyst? You all know, right? S orbital, sp, d, f, those kind of orbitals, and how many electrons can reside in such orbitals? Suppose I'm talking about s orbital. So how many electrons it can accommodate?
Two.
In p? In p orbital, how many electrons?
Six.
In d?
10.
Okay. So in s orbital, we can have 2 electrons. In p orbital, we can have 6. And in d orbital, we can have accommodate 10 electrons. Okay. In case of this kind of transition metals, what happens is this metal has got unpaired d electron. Okay. If it has got unpaired d electron, then these metals are highly active. From unpaired to pair, okay, it will always try to interact with some other, means what is reaction? Reaction means what? Reaction means sharing of electrons, isn't it? So it can share electron or it can accept electron from other molecule or other atom rather. Okay, so that's why nowadays these active metals are basically the transition metals. Transition metal means iron, nickel, cobalt, copper, and zinc also comes under the transition metals. Okay, so in transition metals, how can we synthesize transition metal based catalyst? We can synthesize transition metal based catalyst starting with nickel precursors. Let's assume we are trying to incorporate nickel nanoparticles on a support. Let's say that our support is basically silica. So how can I incorporate nickel? I can incorporate nickel by using a nickel precursor. Precursor means a nickel salt. What could be our typical nickel salt here? We can easily use nickel nitrate. Nickel nitrate is not that expensive. Okay, suppose I want to use one platinum based catalyst. So for platinum based catalyst, I need to use a platinum precursor. So what could be our typical platinum precursor? It could be chloroplatinic acid H2PtCl6, right? This is a chemical formula of chloroplatinic acid. Chloroplatinic acid is quite expensive compared to the nickel nitrate. Nickel nitrate is not that much expensive. Okay, 500 gram cost around 5,000, not 5,000, around 2,500 rupees. But chloroplatinic acid, it's quite expensive, more than 10,000, 12,000 rupees, a small bottle. Okay, so nowadays people are using a method by which, or means transition metal based catalyst, which is basically cost effective. Why is it cost effective? Since it doesn't require that means transition metal based catalyst one can synthesize starting with a nickel. Let's assume we are using nickel based catalyst. So nickel precursor, nickel, what could be our nickel salt? Nickel salt could be nickel sulfate, nickel nitrate. Okay, nickel carbonate also we can use, but in generally in most of the cases, people go for the nickel nitrate salt. Okay, so how can I incorporate nickel nanoparticles on a surface of silica or alumina support? We can easily do it by a method called incipient wetness impregnation method. Okay, after finishing these things, I will teach you how to synthesize a supported catalyst. In that part, I will talk about these things in detail. But for the time being, remember, I have got a support. I will take certain amount of support and I will mix it with a nickel precursor salt solution. What could be the nickel precursor salt solution? Nickel precursor salt solution could be nickel nitrate plus water. Okay, so what we'll do is I'll mix the both of them together like a nickel salt solution plus the support material, and after mixing, thorough mixing, a paste will be generated or formed. Okay, so next I'll do two things. First of all, I'll do the calcination operation. Since here our material is not non-carbonaceous, that's why we don't need any inert atmosphere. Okay, so I'll calcine it at a certain temperature. Again, the calcination temperature will be based on the temperature programmed reduction analysis. Okay, so we'll get a proper calcination temperature. So following the calcination operation, what will happen is nickel nitrate will get converted into nickel oxides. Okay, in the next step would be the reduction step, where what will happen is nickel oxide thus produced during the calcination step will reduce to elemental form like nickel. So first of all, I start with nickel nitrate. Following calcination, nickel nitrate get converted into nickel oxide, and following reduction in the presence of hydrogen, it produces nickel nanoparticles. So these nickel nanoparticles will reside on the surface of silica nanoparticles or alumina nanoparticle seals. Alumina and silica has got very high melting point, like it's above 1000 degrees Celsius. Okay, so that is why what will happen is these materials will remain unaffected during the calcination and reduction temperature. Let's assume we are performing the calcination at a temperature of 400 degrees Celsius. Okay, so at 400 degrees Celsius, if this support material have got high melting point, so these materials will get unaffected, isn't it? They will remain unaffected rather at low temperature. So silica alumina will remain as it is. However, nickel nitrate will get converted into the corresponding nickel oxide at 400 degrees Celsius. Let's assume that the calcination temperature of nickel nitrate is 400 degrees Celsius. Again, I know this since I have worked with nickel nitrate and performed the TPR analysis. So from that analysis, I calculated that the calcination temperature of nickel nitrate to be 400 degrees Celsius. So from my past experience, I'm telling you, this is the calcination temperature of nickel nitrate. If somebody starting means he's carrying out the same reaction, he doesn't have any idea about the calcination temperature, then he has to perform the TPR analysis to get an exact idea about the proper calcination or optimized calcination temperature. So I'm performing the calcination temperature at 400 degrees Celsius. But the melting point of silica alumina, they are quite high, above 1000 degrees Celsius. So at 400 degrees Celsius, they will remain unaffected. Nothing will happen to these support materials. However, nickel nitrate will get converted into corresponding nickel oxide. So
Sir,
now,
which page are you in, sir?
I'm
Only
in,
page
I,
9 is visible.
I'm in this page only, but I'm telling these things. Okay,
Okay.
I'll come to the next page means and I'll explain everything in detail. But for the timing, whatever I'm saying, just listen to it. Okay, so now is the reduction. So reduction we can perform in the presence of hydrogen. Okay, so in the presence of hydrogen, what will happen is nickel oxide will get converted into the elemental form like nickel. So nickel will reside on the surface of silica or alumina. Okay, so this is how we can synthesize a nickel-based catalyst. Similarly, we can use the same procedure for iron and cobalt-based catalyst as well. So instead of using nickel nitrate, in such case, we will be using iron nitrate for iron precursor and cobalt nitrate to means disperse cobalt nanoparticles on the surface of silica or alumina. And remaining steps will remain the same. That means everywhere we'll have to make use of calcination and reduction operations. Okay. So let's assume one thing, I have got a support like this, and on the surface of a support, I have got the dispersion of the active metals. So dispersion of active metals I have shown like this, and this is how I have represented the support. And I am allowing CXHY. CXHY is basically a hydrocarbon gas source. Okay, so I'm allowing CCXHY to penetrate through this catalyst. So what can happen? And let me first of all specify what could be our typical hydrocarbon source. So our typical hydrocarbon source could be either methane, that means CH4, or ethane C2H6, or C2H4, this is ethylene, or C2H2, this is basically acetylene. Okay. So it means we can use propane also, propylene also, but here I have just shown you some examples. One is methane, another one is C2H6 ethane. Propane also we can use as a hydrocarbon source. Okay. Ethylene, we have here C2H4, acetylene C2H2. And we are carrying out this reaction at a temperature between 300 and 600 degrees Celsius. I'm repeating again, I have got a catalyst arrangement like this. This is how I have represented the support. And on the surface of a support, I have got dispersion of active metal. So this is active metal, this is active metal, this is active metal. Okay, so these 6 particles are basically the active metals. And I am carrying out the reaction at a temperature of around 600 degree, 300 to 600 degrees Celsius. And during this reaction, I am purging CXHY through the reaction medium. So what will happen? Is the question clear to all of you? I have got a catalyst system. So catalyst is a supported catalyst. Supported catalyst has been represented like this. Okay, I'm carrying out the reaction at a temperature of around 300 to 600 degrees Celsius. And at this temperature range, I am allowing CXHY to interact with the catalyst system. So there are 2 different possibilities. So what will happen is this also comes under a cracking reaction. Okay, though here we started with 6 carbon, atoms, and we means these are basically called the fragmentations, right? So here we have got a long chain molecule. They fragmented into small chain molecules. One was saturated, another one was unsaturated. But if we are starting with CH4, then what will happen? Or C2H6, C2H4, or C2H2, then what will happen? Then we can see the growth of amorphous carbon on the surface of this catalyst. Okay, this is what I wanted to tell you. Okay, so this also comes under cracking reaction. So this was an example where we have got long chain molecule, but suppose we have got 1 or 2 carbon chain molecule, then what will happen? These are coming in contact with the supported catalyst system, and what will happen? So there are two different possibilities. So here we have got metals, and this is the support. So this will depend on the metal support interaction. So here what will happen, everybody knows that CXHY, they will come in contact with the catalyst system at a temperature between 300 and 600 degrees Celsius, and CXHY will decompose into elemental carbon, isn't it? Methane will crack into carbon. Ethylene will crack into carbon. This is not ethylene, this is ethane. Ethane will also crack into carbon 2C. Acetylene, ethylene, they will also crack into carbon. But there are two different possibilities. Okay, so what will happen is it will all depend on the metal support interaction. So first case would be like metal support interaction. In the second case also, I'll talk about the metal support interaction. When we have got more interaction between the metal and the support, active metal and the support material, then what will happen? We have got amorphous growth of the carbon on the surface of the supported catalyst. I'll show you some of the ACM images that I took by myself. Okay, I also work in the same field, that's why I'm telling you those things in detail. So when we have got less interaction between the metal and the support, then what will happen is these active metals will reside on the surface of the support material. However, there will be growth of amorphous carbon. So this will be the filamentous carbon. Okay, amorphous filamentous carbon. Okay, they look like a filament, or more specifically, they look tubular in shape. I'll show you some of the images just as in just a few minutes. So just for the time being, remember I have got a growth of filamentous carbon like this. Okay, and here what is there is, here we don't have much here we have got more interaction between the active metal and the support, and that is why what will happen is the support means this metal, active metal, will remain adhered to the surface of the support material. However, there will be the growth of amorphous filamentous carbon from the support surface. Okay, so these are the amorphous or filamentous growth of carbon. However, in another case, when there is less interaction between the metal and the support, okay, then what will happen is we'll again have growth of carbon nanotubes, or CNTs. Rather, CNTs are basically carbon nanotubes. So, but these active metals will capture the tips of the carbon nanotubes, thus produced following the interaction between CXHY and the catalyst. You got it? Or should I repeat this part again?
So could you repeat?
Okay. We have got a supported catalyst system. Now you know, right, what is supported system, catalyst system. That means we have got a mixture of support plus active metal, not mixture. If I tell mixture, this is a very crude word, but we need to say that I have got a support. On the top of the support, I have got dispersion of the active metal. So here I have given a pictorial representation of the support. Support looks like this, uneven surface, and on top of this, I have got a dispersion of these active metals. Okay, at a temperature between 300 and 600 degrees Celsius, I am allowing hydrocarbon gas to come in contact with this supported catalyst system. Okay, so now we all understand that what will happen is when we have got the catalyst system, so on the surface of the active surface sites, this hydrocarbon will decompose. Okay, suppose we are talking about 1 or 2 carbon atom, the hydrocarbon atoms, like hydrocarbon molecules, like CH4, C2H6, C2H4, C2H2. On the surface of the active metal, they will decompose or crack into elemental carbon, right? So what would be our active metal? Our active metal is copper, zinc, iron, nickel, cobalt. So there are two different possibilities. If I have got more interaction between the active metal and the support, then we'll have formation of carbon nanotubes following the interaction between CXHY and this supported catalyst. However, these active metals will remain adhered to the surface of the support material, since there is high interaction or huge interaction or much interaction between the active metal and the support. However, there will be growth of filamentous amorphous carbon like this, and they are basically the carbon nanotubes. They have got tubular morphology. I'll show you the morphology in a short while from now. Okay, so for the time being, remember, I'll have filamentous growth of carbon and they are basically tubular in shape. This is one possibility. There is another possibility. So another possibility is what? If we have got less interaction between the active metal and the support, then what will happen is, again in this case also, we have got growth of amorphous filamentous carbon, and the morphology again looks like the tubular. Okay, and however, the active metals will remain adhered, or it will capture the tips of these carbon nanotubes produced. Okay, following the interaction between CXHY and the supported catalyst. So from my practical experience, I can tell you that in this case, like when we can expect to have less interaction between the active metal and the support, when the active metal is transition metals. In case of transition metals like iron, nickel, cobalt, copper, and zinc, we can have this kind of arrangement. Okay, that means we have got a support. On top of the support, we have got a growth of carbon nanotubes. However, the active metals like zinc, nickel, copper, or cobalt nanoparticles, they are capturing the tips of these carbon nanotubes. Okay, this is also a perfect example of catalytic cracking reaction. Okay, however, in this case, we don't have a long chain hydrocarbon molecule. Instead of using a long chain hydrocarbon molecule, we are using a smaller chain hydrocarbon molecules, which are basically methane, ethane, ethylene, acetylene, and so on. Okay, but in case of platinum based catalysts or noble metal based catalysts, in most of the cases, or in the majority, in most of the cases, we have seen that we have got this kind of growth arrangement where platinum or active metals like these active metals, they do not capture the tip of the carbon nanotubes. They remain adhered to the surface of the support material itself. Suppose I have got palladium based catalyst. Okay, palladium supported on silica, we'll get this kind of arrangement. Platinum supported on silica, will get this kind of arrangement. Okay, rhodium will have this kind of arrangement. However, in case of copper, nickel, zinc, iron, okay, and cobalt, we can have this kind of arrangement. Okay, so now let me talk about the properties of the support material. So what could be our support? Support could be of two types. One is carbonaceous, another one is non-carbonaceous support. So what could be our non-carbonaceous support? Non-carbonaceous support would be either alumina or silica, silica alumina, zirconia, and so on. Okay, what could be our carbonaceous support? Carbonaceous support I previously mentioned also, activated carbon, okay, activated carbon fibers, also graphene, carbon nanotubes, they all come under the carbonaceous support material. Support means that supports the dispersion of the active metals. Okay, so what could be our active metals? So our active metals, again, it could be the transition metal or the noble metal. So what could be our typical transition metal? So it could be iron, cobalt, nickel, zinc, copper. But in the case of like not non-transition metals, like for the noble metals, it can be gold. Okay, this is silver also comes under the noble metals. Gold, palladium, platinum, rhodium, Rh also. Okay, we can consider under the noble metals. Okay, so now these things are clear to you. Now let me move to the properties of the support material. So what are the different properties this support material should possess? Okay, so first property is the support material should have medium to high surface area. Just now I talked about the surface area, right? The surface area can be measured in terms of meter square per gram. So surface area, we can measure the surface area of a catalyst by a means technique called BET surface area measurement technique. BET is Brunner, Emmett, Taylor. This is basically named after three different scientists. So one is Brunner, another one is Emmett, and another one is Taylor. So there are three different scientists who invented this process. Okay, so this method is called the BET surface area measurement technique. I'll talk about this method means when the exact time will come. Okay, so for the time being, remember that the support material should possess medium to high surface area. Okay, so why they should possess medium to high surface area? If the surface area is quite less, then we won't have much dispersion of the active metals, right? In order to make the catalyst more active, we need to have more dispersion of the active metals, provided we are talking about transition metal based catalysts. But if we are using active, not active, noble metal based catalyst, then we don't need much loading of the active metals. Okay, suppose we are using transition metal based catalyst, we are using 15% loading of nickel. Okay, the 15% loading of nickel on silica support will give the performance. Okay, and the same performance will be given by 1% platinum on silica catalyst. Okay, so in order to achieve the uniform and homogeneous, and in order to improve the loading of the active metal on the surface of the support material should possess medium to high surface area. It shouldn't possess low surface area. Okay, so how can we measure the surface area? Surface area can be measured by a technique called BET method. So the surface area, by this method, the surface area will determine, and this surface area will come as a, let's assume 200. Okay, the surface area of the material by BET method has been calculated to be 200. So what would be the surface area? The surface area would be 200 meters square per gram. So the unit of this surface area measured by the BET method will come as meter square per gram. Okay. The second property of the support would be what? The second property would be the support material should be less active compared to the active metals. So this is quite obvious. Otherwise, what will happen is, if the support material is too active, then the reactant will come in contact with the support, and the reaction will be performed between the support and the reactant only. Active metals won't have that much role to play. But here in this case, the main role of support is to disperse the active metal. Okay, so that is why if the support is more active, then the interaction will take place between the support and the reactant. Let's assume the CXHY. If the support is quite active, the CXHY will come in contact with the support material, and the interaction will be taking place between both of them, and as a result, we will get certain product, which we don't want. We want the active metal to be more active than the support material. Since what will happen is, the moment I will penetrate or pass CXHY through the active catalyst, means what will happen is, this CXHY will come in contact with the active metal. So on the surface of the active metal, this CXHY will crack or decompose into carbon, not on the surface of the support material. Always remember this. The role of active metal is to decompose CXHY, not the support. Support is just acts as a binder. Okay, so what will support do? Support will facilitate the dispersion of the active metal. However, the decomposition or cracking, whatever you say, of CXHY, that will take place on the catalyst surface side. Active catalyst surface side means on the surface side of the active metal. Always remember this. Okay, and the third important property of the support would be what? The support should have high melting point, so that this material, this catalyst, can withstand at high temperature. Okay, so that means these are the three essential or characteristic features of a support material. Okay, so first means the characteristic feature would be the support material should possess medium to high surface area. Why is it so? If the surface area is quite less, there will be less dispersion of the active metals, which we don't want in case of transition metal based catalyst. Okay, in order to improve the metal loading means active metal loading on the surface of a catalyst, the support must possess medium to high surface area. Okay, the second essential feature would be what? The support should be less active compared to the active metal. If the support is more active, then the interaction will take place between the support and CXHY, not between the active metal and CXHY, which is our desired goal. Okay, so we won't have much decomposition of CXHY. And the third important property of a support would be what? The support should have high melting point. High melting point means it should have high melting point above 1000 degrees Celsius. Otherwise, if the material has got low melting point, then what will happen is there will be aggregation. You understand, right? What is aggregation? Do you know what is aggregation of particles? Means all the particles will clump together at high temperature and they will form an aggregate. If we have got an aggregate formation, then what will happen is we won't have much area for the active surface area remaining for the catalytic reaction to take place. In order to avoid that, we should have a high melting point. The support should have high melting point. So it should have, if it has got high melting point, there is less possibility of aggregation. If we have got aggregation, that means all the particles will clump together and from a large size cluster. So if we have got a large size cluster formation, then we won't have much surface area, available surface area will reduce. If the available active surface area will reduce, there will be less productivity, which we don't want. Right? We always, whenever we perform any catalytic reaction, our objective is to get around 100% conversion. But we have got, if we have got aggregate formation, then what will happen? The most of the active surface sites will be blocked following the aggregate formation. Right? So what will happen is we will have less surface area, active surface area available for the catalytic reaction to take place. Consequently, the conversion of the desired product will decrease, which we don't want. So that is why, in order to avoid that, we choose our support material in such a way so that means the support material satisfies all three. Support material satisfies all three criteria. So what is the third criteria? Third criteria should be it has high melting point. High melting point means it should have melting point greater than beyond 1000 degrees Celsius. If it is less than that, there will be chance of aggregate formation, which we don't want. So in order to prevent aggregation of the large size particles, okay, we'll carry out the reaction at a very low, means suppose we are carrying out a reaction at 500 degrees Celsius and our support material has got a melting point around 500 to 600 degrees Celsius. Then what will happen is this means this support materials will clump together and they will form a aggregate, and active metals will reside inside those aggregates. And it will be very difficult for those gas molecules to penetrate through those aggregates and come in contact with the active metals. It's a problem, right? So what will happen is our, it means desired conversion will decrease, so which we don't want. So in order to avoid that, we'll use a support material, and the support material should possess very high temperature melting point. Okay, so the melting point should be above 1000 degrees Celsius. Okay, so let's take 5 minutes of break and we'll again come back after 5 minutes. I need to drink some water. Okay, so meanwhile you can also take some water. Okay, so let us start again. So was this part clear to you? Or should I repeat this part again? This is not that easy to understand. I understand this, but if you want me to repeat again, I can repeat again. I don't mind repeating it again. Should I repeat again or should I move to the next one? Yes.
You go to the next one.
Okay. So means it was a decomposition reaction, right? So we have got active metal surface sites and decomposition of CXHY will take place, and as a result we'll find growth of amorphous carbon. Okay, so these are filamentous carbon. Why they are called filamentous tubular carbon? So they are of tubular shape. I'll show you some of the same images just now. Okay, so what could be the typical decomposition temperature? Typical decomposition temperature would be around 300 to 600 degrees Celsius. However, this will depend on the type of active metal we'll be using. Let's assume we are using copper-based active metal, copper-based catalyst. So where copper acts as an active metal. So in such case, the decomposition temperature would be quite less. It would be around 350 degrees Celsius. However, if we are using iron or nickel-based catalyst, then decomposition of CXHY will take place at a temperature of around 550 to 600 degrees Celsius. Okay, I'm telling you these things from my own practical experiences. Okay, so the decomposition temperature, we cannot select our decomposition temperature, okay, whatever we want. There has to be some like restrictions. We cannot use any other means any temperature. So for our nickel based catalyst, the decomposition temperature is quite high, like it's around 550 to 600 degrees Celsius. However, if we are performing the decomposition reaction in the presence of copper as an active metal, in such case the decomposition temperature is around 350 degrees Celsius. So the decomposition temperature is based on the type of active metal we are using. Okay, so just now I told you that we have got formation of amorphous carbon and they are having tubular shape. So for base growth also we can have this kind of arrangement. For tip growth we can have this kind of arrangement. As both the arrangement looks nearly the same. However, in case of base growth, the active metal resides on the surface of the support material. However, in case of tip growth, you can see from these images that the active metals capture the tips of the carbon nanotubes. Okay, so this is all based on the interaction between the active metal and the support molecules. Okay, so now coming to the means industry. So where we can make use of this kind of reactions, suppose we want to synthesize carbon nanotubes. Carbon nanotubes has got huge applications, right? They are highly conductive in nature, so this can be used in various applications like in supercapacitors, okay, in lithium ion batteries, okay, in environmental pollution abatement. There are so many other, like in gas sensors also nowadays people are using carbon nanotubes. Okay, they have got tubular structure, they have got high surface area, they are highly conductive in nature, they have got good electron transport property also. That's why they are also being used in photocatalysis, okay, electrocatalysis also. That is why people are basically using carbon nanotubes. So we cannot use carbon nanotubes unless we prepare them. So what are the industries that prepare the carbon nanotubes? So these are means industries like nanomaterial manufacturing industries. They make use of these processes to synthesize carbon nanotubes. Okay, nowadays along with carbon nanotubes, people are generally using graphene based materials. Okay, in Monday's class, I'll ask you what is graphene. So come prepared, okay? Carbon nanotubes, I have told you what is carbon nanotube and how can one synthesize carbon nanotubes. In both the cases, we can synthesize carbon nanotubes. However, in case of tip growth, the active metal will reside on the tip of the carbon, amorphous carbon or tubular carbon. However, in case of base growth, we have got formation of carbon nanotubes. However, the active metals will reside on the surface of the support material. Okay, now I'll show you some of the images that I took for carbon nanotubes. Not here, maybe some other. Let me zoom it a bit. Okay, let me show you some of the carbon nanotubes that I synthesized by myself. This is basically our support material. Okay, so this is graphite. So we have got graphite support material. Okay, try to understand it. So we have got support material. So on the surface of a support material, like here I have used graphite support. So on top of graphite support, I synthesized carbon nanotubes. Okay, so graphite was our support. This is the low magnification and this is the high magnification image of graphite. So this is how the graphite, if I take certain amount of graphite powder and put it under the microscope, this is how the morphology will look like. So here you can see flake type of morphology. However, if you zoom this part, you can see we have got formation of this kind of morphology. Okay, at low magnification image, we can see flake type of morphology. However, if we zoom certain parts, so we can see this kind of shape. Okay, so here it is basically a non-porous type of morphology, means smooth surface, external surface of graphite powder remains smooth. Okay, so this is how the external surface of graphite powder will look like. So what I'll next do is I will incorporate copper nanoparticles on the surface of this graphite. How can I do so? I can do by a method called incipient wetness impregnation method. So in this method, what I did was I incorporated copper nitrate salt on the surface of this. Okay, so we have got dispersion of copper nitrate salt on the surface of this, the external surface of the graphite powder. In the next step, I perform the calcination operation. The following calcination operation, copper nitrate deposited on the surface of this graphite powder will get converted into copper oxide. And next I had to perform the reduction. But remember, since our support is carbonaceous in nature, I couldn't carry out the calcination operation in the air atmosphere. So I had to use nitrogen atmosphere to prevent the burn off of the graphite into carbon monoxide and carbon dioxide. Okay, so next step was to perform the reduction operation. So what was the the purpose of performing the reduction operation? So reduction operation, we converted copper oxides into its elemental form. Like from copper oxide nanoparticles, I produced copper nanoparticles, and those copper nanoparticles resided on the surface of this graphite powder. In the next step, what I did was I allowed C2H2, that means acetylene, to pass through this at a temperature of around 350 degrees Celsius. Okay, so at 350 degrees Celsius temperature, what will happen? We have got growth of this. Okay, so these are basically our carbon nanotubes. Okay, so here you can see the dispersion of carbon nanotubes, right? Compare between this and that. Both the external surface looks different, right? Here, this is for the graphite, and after incorporation of copper nanoparticles, I allowed CXHY. Here in this case, I used acetylene, that means C2H2. Okay, so C2H2 came in contact with copper doped this surface at a temperature of around 350 degrees Celsius. For 30 minutes, I allowed CXHY, means C2H2, to come in contact with this surface for 30 minutes. Okay, so after 30 minutes, I terminated the reaction. Okay, so following this, what will happen is we had formation of this kind of morphology. So what is this? I know these are carbon nanotubes, but for you guys, what I have done is I have zoomed this part. I have enlarged this part, and I have grabbed all these images from scanning electron microscopy. Remember this. With your naked eyes, you cannot see this morphology. Okay, so whenever I have got the material ready, and I take that material and I put it under the microscope and I grab these images. Okay, so these are for the pure graphite powders. And after that, I had copper dispersion of copper nanoparticles on the graphite powder. And then I allowed C2H2 to come in contact with copper doped this surface at a temperature of around 350 degrees Celsius for 30 minutes. Okay, now you can ask me, why did you select the temperature to be 350, and why did you carry out the reaction for a period of 30 minutes? Why not more than that? Why not for 1 hour or 2 hours? Yes, I can carry out the reaction for 2 hours or 3 hours also, but in such case, what I could end up with was I had huge distribution, or I have got like deposition of these materials, like there will be like it will be like aggregation, okay, or it will be like dense growth of carbon nanotubes on the surface of this material, okay, which I don't want. In dense growth, I don't want. I just want uniform growth of carbon nanotubes. If I increase the growth period, like if I increase the time period, then what will happen is I can have dense growth of carbon nanofibers. Already I have got dense growth of carbon nanofibers. I can't, I don't want to get more dense growth. Okay, so whatever growth I have got, I am happy with it. That's why I terminated the reaction after 30 minutes. Now coming to the first question. Why did I carry out the decomposition reaction at 350 degrees Celsius? This was also optimized. I carry out the reaction at 250 degrees Celsius, 300, 350, 400, 450, and 500 degrees Celsius also. Okay, based on the same SEM images, like this kind of images, I selected the temperature to be 350 degrees Celsius. Another thing is copper nanoparticle has got comparatively less melting point. I didn't want copper nanoparticles to get affected with the temperature. Okay, so I didn't want copper nanoparticles to get affected by the high temperature. In order to avoid that, I carried out the reaction at a temperature of around 350 degrees Celsius. But remember, this 350 degrees Celsius temperature is optimized temperature. Okay, unless I optimize, I cannot carry out anything. Nobody will take it. If I say I perform this reaction at a temperature of 350 degrees Celsius, nobody will buy this. I'll have to show this is the optimized condition. Okay, so optimized condition has to be specified. So I have to specify the optimized condition. Then only people will think that, okay, so he has synthesized this at a temperature of 350. So why did he select the temperature to be 350 degree? Why not more? Since they are means from the ACM images, I showed them that if I carry out the reaction at high temperature, then there would be like melting of the copper particles. Okay, from ACM image also you can immediately or easily detect this. So I can show people that yeah, those were the like means copper nanoparticles, melting of copper nanoparticles took place at a temperature beyond 350 degrees Celsius. That is why I choose the temperature to be 350 degrees Celsius. But from this, I can see, since I work in this field, so I know that these are the carbon nanotubes. But for you guys, it would be very hard to understand whether they are carbon nanotubes or some other morphology this material is having. Okay, so that's why what I did was I zoomed this part. Okay, so this is the image of this part. Can you see that tubular morphology, tubular shape? These are all tubular, right? Tubular carbon. Okay, so this tubular structure we have got following the decomposition of acetylene on the surface of copper nanoparticles doped graphite powder at a temperature of 350 degrees Celsius. Okay, so this is basically the carbon nanotubes. I have taken images at various locations. I have got this kind of the similar morphology was observed in different locations also. Okay, so when we carry out these reactions and after that we take the images at various locations to check the reproducibility. Okay, at various locations. So at various locations I have taken these images, and this is the low magnification, this is high magnification image at certain point, and this is also a low magnification and the corresponding high magnification image at other point. Okay, so at this point I have grabbed image like this, at this point I have grabbed image like this. Okay, so these are all tubular structure, right? So now I need to show you that these are basically means the decomposition of CXHY followed the tip growth mechanism. By ACM analysis also we can show it, but it is very complicated to show using the ACM analysis. There is another analysis called transmission electron microscopic analysis. By this analysis, one can show that yeah, so this here is our active metal. I'll show you in a short while. So just a few minutes back, I talked about the energy dispersive X-ray spectroscopic analysis. I told you, right? So to detect the presence of a metal on the surface of a support, we make use of this method. So here you can see the energy dispersive X-ray spectroscopic analysis of this material. Okay, so you can see carbon, oxygen, nitrogen, and copper. So where does copper come from? Copper comes from the copper nanoparticles. Okay, and carbon comes from the graphite. Nitrogen also, little bit nitrogen is also found in the graphite material. So and oxygen. Okay, so carbon and oxygen came from the carbon nanotubes and the graphite powder, and nitrogen came from the graphite. Okay, so it depends on the synthesis route also. So the way people synthesize this graphite, this contains certain amount of nitrogen. So by this, I proved that the growth of carbon nanotube was facilitated by the copper nanoparticles. So these are basically the elemental mapping showing the distribution of different particles like copper nanoparticles, carbon, nitrogen, and oxygen on the surface of this material. Okay, so this is the energy dispersive X-ray spectroscopic analysis, but this is the elemental mapping analysis, and this is the energy dispersive X-ray spectral analysis. This is the spectra, right? So here I have got spectra like this. So here we have got copper nanoparticles, carbon, oxygen, and nitrogen. So copper comes from the copper nanoparticles deposited on the surface of this material. Okay, carbon and oxygen came from graphite and carbon nanotubes, and nitrogen comes from the graphite powder. Okay, so now I'll have to prove that the growth means is the growth of carbon nanotube is governed by the tip growth mechanism. So I can easily show this. So here I have taken a low magnification image, and this is the high resolution TM image. This is the carbon nanotube. Now I'm talking about one single carbon nanotube. It is very difficult to grab these images, you know. Okay, so it looks very simple to see, but grabbing these images is quite complicated using a transmission electron microscopic image. Okay, so this is our carbon nanotube. Look at the color contrast. This is the tip of the carbon nanotube, and here you can see this, right? So this is basically our copper metal. Okay, look at the color contrast. So this is basically dark. Metals always, they are very dark when I take the transmission electron microscopic images. So this is a dark one, right? So this particle is basically the copper nanoparticles, and this is the carbon nanofiber. So the tip of the carbon nanofiber. Okay, so this is basically the tip of the carbon nanofiber, and this is captured by the copper nanoparticles. So here I have zoomed these copper nanoparticles, and I perform some other analysis as well, but for the time being, you don't need to go into those things. Okay, so now is this clear? How can one see whether it is tip growth or base growth? Anything? Any further questions from here? I'd love to answer to your questions. If you have got any questions, any doubts from here. But remember, you need to remember these things. Okay, I'll talk about these things while teaching you the catalytic cracking also. Any questions from this side?
No.
Is it clear to all of you? How the growth of carbon nanotube taking place, whether it is tip growth or base growth, how can one determine this? How can one confirm this rather? Okay, how can one find out the existence of copper nanoparticles? What measurement technique one should use? These are the things you need to remember. If you remember these things, then you don't have to memorize things like what is catalyst, what is supported catalyst. Okay, like this. Okay, these are tubular structures. So these are basically the carbon nanotubes. And here I have taken this is one analysis. This is called the scanning electron microscopic analysis. And this analysis is called the transmission electron microscopic analysis. This analysis is very complicated. Okay, so it was very difficult for me to grab this image. Like also means taking one single carbon nanotube and showing the existence of copper nanoparticles on the surface, on the tip or at the tip of the carbon nanotube is quite difficult. But luckily for me that I got this image. Okay, so here it clearly shows you the growth of carbon nanotubes in this case was facilitated by the tip growth mechanism. Okay. Okay, so now it is clear, right? What is tip growth and what is base growth and all. So this thing happens for the catalytic cracking. But remember that this catalytic cracking will be performed in the presence of a catalyst. But here the carbon number would be quite less. It would be 1, 2, 3. Maximum n is equal to 3. Sometimes we go for 4 also, but with the carbon number n is ranging between 1 to 3 is best for this kind of reactions. Or for the production of carbon nanotubes, people generally don't go for like high carbon number, like methane, ethane, propane. So means in very minimal cases, I saw people using butane, okay, as a hydrocarbon source to grow carbon nanofibers. But in most of the cases, we'll either use like CH4, that means methane is very popular, ethylene is also very popular, acetylene is also popular. Because these are the three means hydrocarbon source we generally make use of to synthesize carbon nanotubes on the surface of any catalyst. Okay, so here I talked about the non-carbonaceous support, but there I showed you the ACM images where means carbon nanotube was grown on the surface of a carbonaceous support. So graphite is carbonaceous in nature, right? So I wanted to synthesize this material for supercapacitor application. Since graphite is also highly conductive, carbon nanotubes is also highly conductive. So synergisty between graphitic carbon and coming from the CNT and the graphite. Okay, that facilitated the okay. So the next reaction is called the cyclization reaction. This is the last reaction I'll be teaching you today. Cyclization reaction will also make use of cyclization reaction in petroleum refineries. Okay, so here we have started with means a normal paraffinic compound, as the name suggests. Here also we'll be producing a cyclic compound starting with a normal paraffinic compound. Okay, so what is our simplest cyclic compound? What could be the simplest? Can anybody tell me some of the examples of cyclic compounds? Yes, cyclohexane I have already shown you. So give me some examples of cyclo compounds. Huh?
Benzene.
No, benzene cannot be treated as a cyclo compound. Benzene is an aromatic compound. Okay, while teaching you the petroleum refinery, I'll show you that paraffinic compounds, saturated compounds, unsaturated compounds, naphthenic compounds. Okay, so naphthenic compounds are basically the cyclic compounds. And aromatic compounds are basically benzene. I mean, benzene is the simplest aromatic. Though benzene has a ring, but it has got alternate double bonds, right? But benzene cannot be treated as a cyclic compound. So methyl cyclohexane, methyl cyclopentane, right? So these are basically the cyclic compounds. Cyclic compounds are the non-aromatic compounds. So in case of aromatic compound, there has to be alternate double bond, right? But in case double bond, single bond. But in case of cyclic compounds, all the bonds are basically the single bond. Means all the carbon atoms in a cycle, they are like bound by a single bond. Okay. So cyclic compounds are basically the naphthenic compounds. I'll talk about those compounds while teaching you the petroleum refinery engineering. Okay, so here we have means in petroleum refinery, one of the famous reactions. This comes under one of the famous reactions in petroleum refinery. This reaction is called the cyclization reaction. In case of cyclization reaction, we start with a normal chain compound like normal paraffinic compound. It shouldn't have any double bond or triple bond, so it's a normal paraffinic compound. In the presence of a catalyst, nickel-based catalyst, sometimes in petroleum refinery we are using platinum-based catalyst also in order to improve the yield of the desired product. So from normal paraffinic compound, we are getting cyclic compound. Like this is cyclohexane. Since here we have got 6 carbon, right? 1, 2, 3, 4, 5, 6. So we are getting cyclic in cyclohexane. Suppose I have got 7 carbon here in the chain. So what would be the typical cyclic compound? Think of it and give me the answer. Here I have got 6 carbons, so I have ended up with a cyclic compound called C6H12. This is cyclohexane. Let's assume I have got a means like normal compound, paraffinic compound, where 7 carbon atoms are there. So following the cyclization reaction, what would be the typical product in this case? Again, bhai?
C7H14.
No, you'll have to tell me the structure. Like this. I have represented it like this, right? So you'll have to tell me what modification will be there in this structure.
So there'll be a methylene group added, I guess.
Exactly. There will be one methylene group that would be added to any of these carbon atom. Okay, there are 6 carbon, right? So with any of these carbon atom, one methylene group will be added. Okay, so this is called the cyclization reaction. For the timing, remember what is cyclization reaction? This reaction is conducted at a temperature of around 450, 470 degrees Celsius temperature. Okay, So this is the cyclization reaction, and in case of cyclization reaction, either transition metal based catalyst one can use, or platinum based catalyst also we can make use of. Okay, since in petroleum refinery nowadays people are generally using platinum based catalyst, sometimes rhodamine based catalyst is also considered for the cyclization reaction. Okay, so this is what the cyclization reaction is all about. Okay, so since we don't have time left, so we'll stop here again. So again, we'll reassemble on coming Monday. Okay. Okay, thank you guys.
Thank you, sir.